All right, so let's look at your opener. We're told we've got this particle and it begins here at negative 2, 2. So here is our initial point. Where we started. It moves out here to 4, 2. And then it ends up over at negative 1, 2. And so over there at negative 1, 2 is our terminal point, where we ended. And we're finding the displacement. And we talked some about displacement yesterday. Displacement is how far did we move from where we started to where we ended. Well, I can look at this picture. I can think of this as a simple number line. That's really all we have here. Because all of those y values are 2, we just have a simple little number line. And we moved from negative 2 to negative 1. Really only paying attention to these x values since the y's are all the same. Well, moving from negative 2 to negative 1 is moving 1 unit to the right. So our displacement is positive 1. Now, if you would prefer to do this as a subtraction algebra problem as opposed to a picture problem and being able to figure out that displacement, you can. There's nothing wrong with that. We ended at negative 1. So take where we ended, subtract where we started. We started at negative 2. And when I subtract those, I'm going to get positive 1. There's nothing at all wrong with that as we deal with our displacement. Any questions at all there with your opener? Okay, well, let's take that same little problem and let's talk a little bit about distance. And let's talk about the difference between displacement and distance. Now, distance is something you know a lot about and have done quite a bit of before. Right? Distance is always positive. That's important. Displacement is not. Distance is how far did you move total, right? The total amount of movement. The simplest way to illustrate that is if you leave your house in the morning to come to school and tomorrow afternoon you go back home, your displacement would be 0. Because how far from where you started to where you ended, it's the same thing. But your distance is not 0. Right? Distance is going to take into account changes in direction. So if we use the same example we just looked at, that we have this little particle, and it started at negative 2, 2. I'm going to abbreviate initial point here. And then it moved over here to 4, 2. And then it ended over here at negative 1, 2, our terminal point. The distance we've traveled is very different than the displacement. Because we came out through here and we went to the right. And we went to the right 1, 2, 3, 4, 5, 6 units. But then we turned around and we move back to the left 5 units. So my distance is that total amount of movement. Well, I went to the right 6 units. I went to the left 5 units. And so the distance I've traveled is 11 units. Centimeters, feet, I don't know what that is. A big difference from the 1 unit of displacement we had, right, in our distance. Now, again, I could have done this as a subtraction problem. If we say here that we begin and time is 0, let's say it takes us 1 second, we get out here to 4, and 2 seconds, we stop here. So here's our position when t equals 0, our position when t equals 1, and our position when t equals 2. We could have said, all right, I went to the right for 1 second. So let me find that displacement. But I don't really care whether that displacement's positive or negative. So I'll do absolute value. And then I'll find the displacement while I move to the left. And again, I don't care whether I moved left or right. And we could calculate. Well, S of 1, I was at 4. S of 0, I was at -2. S of 2, I was at -1. S of 1, I was at 4. I still have 6 units plus 5 units. That's not going to change if we do it as an algebraic problem as opposed to a picture problem. When we're dealing with distance, I need to know an answer to a very important question. Did I change direction? Did I change direction? I can't only deal with where I started and where I ended. Now, are there any questions there in the difference in displacement and direction? Or distance, where I need to know direction? Okay. Then I would like to give you about 6 minutes to try numbers 3 and 4. Okay. In number 3, you're going to find the displacement of the particle during the first 4 seconds. If the particle is moving along a line so that its position for any time t greater than or equal to 0 is given by our position function, t squared minus 6t plus 5. And then in number 4, instead of finding the displacement over the first 4 seconds, you're going to try to find the distance over the first 4 seconds. Let's look at numbers 3 and 4. Now, it's not a requirement, but I think it's very, 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 very helpful if you'll take and draw a picture. We've got this particle moving for 4 seconds. Well, we're looking at it for the first 4 seconds. And it's moving along a line. So give yourself just a simple little line so you can visualize what's happening. So here's our little number line, and we're going to put our little particle on it. So we need to first of all know, where are we on this number line? We're going from t equals 0 to t is equal to 4. And those are, of course, measured in seconds. So the first thing I need to know is, well, when I start, where am I on this number line? What's my position? That position is given by this position equation. So my initial point where I'm going to start is just going to be s of 0. So 0 squared minus 6 times 0 plus 5. We're going to start out here at 5. But if I'm going to find the displacement, I need to know, where am I going to end? Where's my terminal point? Well, the particle may not have ended, have stopped moving at 4 seconds, but that's where we're going to stop watching it. So we need our position when t is equal to 4. And we get 16 minus 24, or negative 8 plus 5, which is going to be negative 3. So I started at 5, I ended at negative 3. Okay? So I can look at this picture and I can look and see, I moved left, and I moved to the left 1, 2, 3, 4, 5, 6, 7, 8 units. So my displacement is negative 8. And all I needed to do is be able to draw out a picture. Where did I start? Where did I end? Now, if you don't want to do it with a picture, it's okay. You could do displacement, and I'm going to abbreviate here. S of 4 minus S of 0, where we ended, minus where we started. We would get negative 3 minus 5. You'll get negative 8. There's nothing at all wrong with that. But we have our displacement. Now, there's a lot I don't know about this particle. I mean, I know it started at 5 when t was 0, and I know when t was 4, it stopped at negative 3, but there's a lot I don't know in between there. How fast did it move? Did it go to the right and then to the left, or to the left and then to the right and then to the left? There are a lot of things I don't know. So before we look at number 4, I want you to grab your calculator for me. And in fact, we may use your calculator to do something you haven't really ever done before. So I'm going to share my calculator screen with you here. And what I want you to do in your calculator is, first, I want you to go to mode. And we're going to change our mode from function to parametric. Probably not a mode you've used a whole lot. So just arrow down there till you highlight parametric and hit enter. Now, you talked a little bit in 10th grade about parametrics and writing a function in terms of horizontal and vertical components, in this case, in terms of other functions, two other functions in terms of another variable. And we're going to use that to help us here with our motion of our particle. Now, when I'm on my home screen, nothing looks any different, but when you go to y equals, things are going to look different. In our x equals, I want you to put our position equation, t squared minus 6t plus 5. Now, I actually mentioned to you yesterday, typically for our position function, we'll use either s or x of t. This is why we would use x of t, because we're going to write it as a parametric. And then in y equals, I want you to put 3. Now, there's nothing special about 3. This is just so that we aren't sitting on our x-axis. It makes it a little easier to see. So I moved it up to y is equal to 3, so it's easy to see there on our graph. Now, before you hit graph, arrow over here to the left, and we're going to change not our color, but you probably have that little line. And I'm going to hit the right arrow till I get this little circle, like a little bouncing ball with a dash. And then I'm going to tell it okay. And that's going to allow us to do two things. It's going to allow us to see a circle to represent our little particle. And then the little dash will show us the residual kind of the movement of this as we went. But before we hit graph, go to window. And let's adjust our window a little bit. We now have some values for t, for time. So we're going to adjust those to go from 0 to 4. And then I want to adjust our t-step. I want to slow this down just a little bit so it's easier for us to see. So decimal 0, 1, 1/100th. Our x-min and x-max and y-min and y-max, we can kind of use our standard there and go from -10 to 10. All right, and then I want you to hit graph. And you'll be able to see the motion of this particle. So here you can see us starting out here at 5. We're moving towards the left. Time is passing as our little particle is moving. It looks like I'm kind of slowing down a little bit here. Going very slow now. But now I notice I'm moving back to the right a little bit. So there's kind of our number line that we're moving along. But we are able to see some things about this little particle that we couldn't see, right, when all we did was graph where it started and where it ended. We couldn't see it moved out here past where it ended and it moved, turned back. We couldn't see it speeding up and slowing down. Right? We can see those when we graph in parametric mode in our calculator. And so parametrics are a really helpful, useful piece for seeing the motion of our particle. And that helps us a little bit with part number 4 that you worked on. In number 4, we're finding the distance of our particle over the first 4 seconds. So on our number line, we've still started in the same place. We still started out here at 5. We still ended out here at -3. That hasn't changed. But now we know a little bit more about this particle, and we've got to answer one of those really important questions. Did this ever change direction? Anytime I want to know distance, I've got to know, did the particle change directions over the 4 seconds that we have? Now, you could randomly plug in time values from 0 to 4 and see, okay, did we ever end up at a position, farther over than -3? But that's not a very effective way to do this. So we want to go back to what we talked about yesterday. Yesterday, when we talked about relationships, we talked about a way to know if we changed directions. That when our velocity was positive, our position was increasing and we were moving to the right. And when our velocity was negative, our position was decreasing and we're moving to the left. So velocity will tell us about our direction. So in our little problem, if we want to know if we're changing direction, we want to know, is there a change in the sign of our derivative of velocity? We want to know, okay, are we moving to the left? Our velocity, our derivative of our position, would be negative because position would be decreasing. And we need to know about when we're moving to the right, when our velocity is positive, our derivative of position. So we're going to have to know S prime of t. Now, fortunately for us in this particular problem, it's not a complicated derivative to take. Function f, s, is just t squared minus 6t plus 5. So we can simply take the derivative of each of those pieces. They are our power rule. The derivative of t squared is 2t. The derivative of negative 6t is negative 6, and the derivative of 5 is 0. And so we just have a couple inequalities we need to solve. 2t minus 6, our velocity. When's that less than 0? 2t minus 6, when's that greater than 0? Now there's several options for how we could solve this. Because this is linear, you might just solve a linear inequality. Add 6 to both sides and divide by 2. And we have that our particle's moving to the left. For the first 3 seconds, we need to remember we do have time values that are greater than or equal to 0. Anytime after 3 seconds, we're moving to the right. Notice there that our velocity is equal to 0 when t is equal to 3. That's where we have this change in direction. And if you noticed, as our particle moved when we looked at it on our calculator, we had this particle that as it moved, it slowed down and then stopped momentarily. That stop was at 3 seconds. Now, you could have dealt with when your particle was moving to the left or right really in 3 different ways. One, because it was linear, you could have just solved. You also could have just taken and drawn a graph. It wasn't a hard graph to draw. It's just a little line. It's got a y-intercept at negative 6. It's got a rate of change of 2. You could have just drawn you a little graph of that line. And then look at that line, and you could have told, well, when's that greater than 0? When t is greater than 3. When's it less than 0? Or you also could have made a sign chart. And if this had been something that wasn't linear, I probably would have made a sign chart. Now, if I'm going to make that sign chart, I have to make sure I label it. What is this a sign chart for? And I'm really only interested on that sign chart when I'm equal to 0. That's where I'm going to have changes potentially in signs. And I can just plug in, something less than 3 like 2. 2 times 2 minus 6 is a negative value. Something bigger than 3 like 5. 2 times 5 minus 6 is a positive value. And I'd be able to know when my velocity is positive, when it's negative, just based on a little sign chart. So now I can think about my picture. I know that I started out at 5 and I was moving to the left for 3 seconds. And I've got to know, oh, wait a minute though. I don't know where I stopped. I know I moved for 3 seconds. I need my position after 3 seconds. I need to know where on the number line did I stop. I know I moved to the left for 3 seconds, but I don't know where I was. So I'm just going to plug in t squared minus 6t plus 5. We have 9 to minus 18, negative 9, plus 5, or negative 4. So now I can better draw my picture. So I actually moved to the left those first 3 seconds all the way out to negative 4. And then I turned around and I changed directions and I stopped out here at negative 3 on my number line. Oh, well, okay. So that means to the left, I moved 9 units. And then I moved 1 unit to the right. So my distance is how much did I move to the left? 9 units. Plus how much did I move to the right? We moved a total of 10 units. A total of 10 units. I have to know about whether or not I changed directions, right, over those first 4 seconds. Now, you don't have to draw this picture on a number line. I can do it algebraically. My distance is still, okay, how far did I move to the left? How far did I move to the right? How far I moved to the left would be, well, for the first 3 seconds, I moved to the left. Let me find that distance. I don't care about direction, so find displacement. You could do s of 0 minus s of 3 because we're dealing with absolute value. And then I only moved to the right for 1 second. Well, 1 second in the first 4 seconds. So I have s of 3. I was at negative 4 on the number line. S of 0, I was at 5. S of 4, I was at negative 3. I still get 9 plus 1. I still get a distance of 10 units. This is not a requirement to draw the picture, but it'll help us to understand what's going on. Now, are there any questions there? With 3 and 4, we're dealing with the difference in displacement and distance. All right, now while we have a nice picture for what's going on and we have a better idea for this particle that we changed directions, there's still a lot I don't know about this particle as it moves. I mean, I know when it moved to the left and when it moved to the right, but I don't know how fast was it going? Was it speeding up? Was it slowing down? So we want to finish up today talking about one more vocabulary word, and that is speed. Now, speed and velocity are 2 very different things. We talked about velocity yesterday. That velocity is the rate of change of our position. It has both a length and a direction. That makes it a vector. Vector v for velocity. How far did it move? And what direction did it move? If we want to know speed, speed is simply the length or the magnitude of velocity. The magnitude or length of velocity is just our absolute value. You might sometimes see it with the double bars. That's our speed. The magnitude or absolute value of velocity. So one great way to deal with speed sometimes is to draw a picture. So here we have a graph of velocity with x-intercepts out here at -1 and 3. I would like you to draw a graph of speed, the absolute value of velocity. That's a transformation you dealt with in the 9th and 10th grade. So I want to give you just a couple minutes to draw a graph of speed. And then once you've drawn that graph, I want you to use that and answer, when is the speed of the particle increasing? When is the speed of the particle decreasing? Use your graph to answer that question. So our graph of speed. Well, if speed is the absolute value of velocity, we can just take a few little speeds, like, out here when x is -2, we've got this speed value right around 4. Well, the absolute value of that is still going to be 4. So anywhere I've got speeds that are velocities, that are positive, speed's not going to be different. So my graph's going to start out, and it's not going to look any different at all than velocity. But then I'm going to get down here where I have negative velocities, right down here. And I'm going to have to take the absolute value of those, and they're going to become positive. I'm going to reflect those over the x-axis. So we're going to take and fold this graph up above the x-axis. We're going to reflect it over the x-axis and then finish drawing our velocity again. And now we have a graph of speed, and it should be really easy to look at this and say, okay, speed, when's it increasing? I'm going to highlight it. I can look and see, when are the y values getting bigger and bigger and bigger and bigger? Speed is increasing from -1 out to 1 and from 3 to infinity. Now, when we deal with increasing and decreasing, we can use brackets or parentheses. I'm actually going to use parentheses here. That will be the more common piece that we will use. We are having our speed increase from -1 to 1 and from 3 to infinity. And then we're decreasing from -infinity out to -1. And from 1 to 3. Now, a graph of speed is a great way to tell where speed is increasing and decreasing. Now, there is a drawback. Well, two drawbacks. Number one, sometimes the graph of velocity is not so easy to draw. And so then using our transformation for the absolute value, the magnitude is going to be harder. And if I'm trying to prove or justify when speed is increasing and decreasing, I can't just draw a graph. I can't discuss that based on a graph. So I'm going to go back to our picture we ended with yesterday, where we've drawn velocity, acceleration, and position all together. And we're going to try to take right there and look at, well, could we use those graphs to figure out when speed is increasing, when speed is decreasing? So let's start with when speed is increasing. And I'm going to take and I'm going to highlight, because we know this answer. we know speed is increasing. This is the graph we just looked at. Speed is increasing from -1 to 1 and from 3 to infinity. And we know speed is decreasing from -infinity to -1 and from 1 to 3. So we're going to take and we're going to highlight our velocity and acceleration graph when speed is increasing. So from -1 all the way out to 1 and from 3 to infinity. Now, the first thing there to notice is by itself, velocity is not enough information to tell me about speed because I got some of that velocity that's negative and some of that velocity that's positive. I've got some velocity that's decreasing. I've got some velocity that's increasing. By itself, velocity will not tell me speed. Okay, well, let's highlight here our acceleration from -1 to 1. So I've got some acceleration that's negative, and then from 3 to infinity. Again, I've got some acceleration that's negative. I've got some acceleration that's positive. Acceleration by itself is not enough information to tell me about speed is increasing. But I do notice something when I highlight those. From -1 to 1, velocity and acceleration both have the same sign. They're both negative. And from 3 to infinity, velocity and acceleration have the same sign. Hey, that gives me something I can look at. I could look at velocity and acceleration and note that they have the same sign. Now, that shouldn't come as this big surprise. Velocity is a vector. So we might have our velocity vector moving to the right. Acceleration is also a vector. So if our acceleration vector is also moving to the right, then these two things are working together. And so our speed is increasing. Think of this from real life. You stopped at a stop sign. And then it's time to go, and so you push the gas pedal. Well, you're moving forward. Velocity is positive. But your change in velocity is increasing, so acceleration is positive. And you look at that little dial on your speedometer, and it's going up, 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 up. Velocity and acceleration are working together. Speed is increasing. But then we look at velocity from -infinity to -1, and we see velocity is positive, but acceleration down here is negative. Oh, velocity and acceleration have different signs. I've got those vectors working against each other. And speed is decreasing. I'm slowing down. I was moving forward. My velocity was positive, but somebody pulled out in front of me, so I slammed on my brakes. I was still moving forward. My velocity was still positive, but my acceleration now was negative, and that speedometer began to go down. I was slowing down. My speed was decreasing. If I want to justify or prove about speed, I have to look at both of the signs of velocity and acceleration. Now, I tried to put all that for you in your notes in kind of a nice, convenient place, right? Where we talked about position function yesterday, its derivative of velocity, that we could tell that velocity was positive when position was increasing, velocity was negative when position was decreasing. Right? We used that today, that velocity was positive, we were moving to the right because position was increasing. Velocity was negative, we were moving to the left. And when velocity was 0, we were at rest. We talked about the derivative of velocity being acceleration. And then today we talked about speed. Speed is increasing, right, when velocity and acceleration have the same signs, or it's decreasing when velocity and acceleration have different signs.